You know, when physicists smash particles together at almost the speed of light, what's left behind is just this chaotic spray of energy and debris. So how on earth do you turn that chaos into a discovery? Let's dive into the fascinating puzzle of how scientists actually define the indefinable.
Right. So you've got this incredibly messy aftermath from a collision. And that's really the central challenge, isn't it? How do you find a meaningful signal inside all of that noise? I mean, how do you even begin to describe what you're seeing? Well, the answer is to look for patterns, because the debris, it isn't completely random. It tends to spray out in these focused streams that we call jets. You can almost think of them as the fossilized footprints of the quarks and gluons that were created in that first fiery moment. Finding these jets is really the very first step to understanding what just happened. But here's the catch. Not all methods for finding jets are created equal. They have to pass this absolutely crucial test called infrared safety. And it's a pretty simple idea at its core. Your method shouldn't be fooled by ghosts. If a particle with almost no energy pops into existence, or if two particles are traveling perfectly parallel, it shouldn't completely change your final answer.
And I want to be clear, this is not just some minor academic detail. If your algorithm isn't infrared safe, the theoretical calculations literally fall apart. The predictions just become meaningless infinities, and any comparison between your theory and your experiment becomes totally impossible. The stakes are incredibly high. So, how did scientists first even try to tackle this? Well, they started with a really logical, almost common sense idea, the cone algorithm. It's a very intuitive way to start grouping particles together. The process is wonderfully simple, really. First, you find the most energetic particle you can, and you call that your seed. Then you just draw a circle, or a cone in 3D, of a set size around it and say, okay, everything inside this cone is one jet. You add up all their energy and momentum, and voila, you're done. Simple, right? Well, as the source material puts it, this elegant idea was, unfortunately, a little bit too simple. It had this hidden weakness, a problem that wasn't obvious at first, but would turn out to be a fatal flaw. And this is where our story takes a dramatic turn. Let's see exactly how this simple idea breaks down, all because of one tiny troublemaker particle. So imagine a really simple scenario. You have two high-energy particles. We'll call them partons. They're far enough apart that any sane algorithm would look at this and say, yep, that's two separate jets. So far, so good. But now, physics being what it is, a third, very low-energy particle, what we call a soft gluon, can just pop into existence right between them. It has almost no energy, so it really should be completely irrelevant. But it's not. This tiny troublemaker can act as a new seed. And because it's positioned perfectly in the middle, it can now draw a cone that captures both of the original high-energy particles. So all of a sudden, your two jets have become one. The result is completely different. And that's the whole problem, right there. The algorithm was totally fooled by a tiny, insignificant emission. It fails the most important test. It is not infrared safe, and that means it's just not reliable enough for serious physics. But physicists didn't just give up on the whole cone idea. That's not how science works. Science is a process of iteration. They tried to patch it, to find clever ways to solve this troublemaker problem. The first fix was something called the midpoint cone, which basically added more potential seeds in the empty spaces between jets. It helped, but it wasn't a complete solution. And eventually, they developed size cone, a seedless version that finally achieved infrared safety by getting rid of those problematic seeds altogether. But even as the cone was being perfected, a completely different, and some would say more elegant philosophy was emerging. It was a whole new way of building jets from the ground up. And this slide really gets at the fundamental difference. Cone algorithms are top-down. They impose a fixed geometric shape onto the data. The new idea, the KT family of algorithms, is totally bottom-up. It doesn't assume a shape at all. Instead, it lets the jet build itself, one particle at a time. The logic here is just beautiful. The algorithm calculates a special kind of distance between every single particle. And this isn't just about space. It's a distance based on the actual physics of how particles radiate. It finds the two particles that are closest in this physical sense, and it merges them. Then it just does it again and again and again, iteratively clustering particles based on their history. It's so elegant because this process actually mimics the way jets form in nature. It's like rebuilding their history in reverse. So I know this might all seem like a really abstract, super technical debate, but the choice of which algorithm you use, well, it has profound consequences for our ability to actually make new discoveries.
Because at the end of the day, these algorithms are the bridge. They're the only thing connecting a wild, chaotic experiment to a precise mathematical prediction. And if your bridge is flawed, if your jet definition is wrong, you just can't trust your results. Period.
1. That's how many flawed assumptions it takes to completely invalidate an entire analysis. Getting this one definition right is one of the most fundamental make or break tasks in all of particle physics. And this is not just theory. These sophisticated infrared-safe algorithms, like KET, are the standard tools. They're used every single day at places like the Large Hadron Collider. They're the unsung heroes that turn terabytes of chaotic data into discoveries, like the Higgs boson. Which kind of leaves us with a final thought, doesn't it? We've just seen that the very act of defining what you see is an incredibly complex scientific challenge in itself. It really makes you wonder, if this is what it takes just to see clearly, what amazing discoveries might be hiding just beyond our view, waiting for the next brilliant algorithm to finally bring them into focus.